We are really excited to have Dr. Charles Greenspon joining us today to discuss his research using intracortical microstimulation. Charles is a research assistant professor at the University of Chicago, where he uses ICMS to restore the sense of touch to individuals with spinal cord injuries. His research focuses on designing spatiotemporal patterns of ICMS such that the sensations are both intuitive and informative. Charles, thank you so much for joining us today. I will pass the time over to you shortly, but first, a note to our audience. We'll take questions at the end of the discussion. Please feel free to submit your questions as Charles is presenting, and we'll get to as many as we can following his presentation. Take it away, Charles.
Great. Thank you so much for having me. Let's see if I can get this working. I assume everyone can see my screen. As Vas said, my name is Charles Greenspon. I work as part of the sensory-motor bionics group at the University of Chicago and with the cortical bionics research group, which is a collaboration between University of Chicago, Northwestern University, and University of Pittsburgh. And before I sort of start, I'd really like to emphasize the fact that this is an enormous collaboration that is composed of nearly 10 PIs, like 100 total grad students, postdocs, engineers, and the overall program of research has been going on for over a decade. And without all of their contributions, none of the work I'm going to present today would have been possible. And in addition to all of those people, if we had no people who were volunteering their time to do this work, there would be no science at all. And so we have to date implanted 6 participants, but I'm only going to present work on the 4 of them. And they truly, come in up to 12 hours a week for, in one case, 10 years now. And so really, they make it easy for us to do the work, and they make it really enjoyable, and their efforts are worth more than pretty much anyone else's. Talking about the participants, the 4 I'm going to talk about today, here are some MRI scans just to situate everyone. The dashed line in the middle is the central sulcus. So this is their contralateral hemisphere to where we're implanted. All of our participants are right-handed. We've implanted the left hemisphere. And the sort of colored rectangles show the location of 4 Utah arrays that are implanted. On the left in motor cortex, MC, there are 2 100-channel arrays. And on the right, on the rectangular ones in somatosensory cortex, there are 2 30-electrode arrays. And so all of our participants have the same arrays. And that is particularly important. And a lot of people who do more basic science will know that it's almost impossible to do a study with an N of 1. And the biggest benefit of having this large consortium is the fact that we can implant multiple people, replicate our experiments across participants and sites, and ensure that the experiments we do are sort of like translationally and clinically relevant. Now, the focus of my talk and my specific interest, as Navas said, is using intracortical microstimulation to restore the sense of touch. And you might wonder why touch is important. And so many of you might have seen this video. The task here is for the woman to pick up a match and light it. And you'll see in the first video, she's able to accomplish this in like 2 to 3 seconds, right? It's trivial. She can pretty much do it as long as it takes me to say it. However, if you just numb her fingertips with some lidocaine, okay, all of a sudden this task becomes incredibly difficult. She struggles to pick it up. She can't really orient the matchstick once it's in her hands. And then even when she can do that, she can't really apply force to the matchbox and strike it properly without like adjusting it a couple times. And the thing to note here is that she has perfect vision of the object, her grasp, and the interaction that's occurring, okay? The only thing that's lacking is touch. And if we think about how a participant might use this device, they wouldn't only lack touch, but they might not have perfect motor control, and they might not have proprioception either. And so all of these things need to come together for a prosthetic limb to be functional and useful and come close to the level of performance that natural humans or humans who are completely intact can achieve. And so that's like really the scope of like these brain-computer interfaces is to restore that. And in particular, I'm going to focus on the tactile part of it. And matchsticks aren't the most commonly used thing that we use our hands for. There's a couple other examples. The first of which is perhaps, we use our fingers for very fine detail, and the extreme version of that is Braille, right? Our fingers are so sensitive that you can read Braille. You might also, pet your dog. This is my dog. He's laying on my lap right now. He's like soft and fluffy. And as I go about and I explore the world, my desk is hard, my dog is soft, and we get all of these features that tell us about the environment and the objects that we're interacting with. And on the other end, there are objects that we don't want to interact with because they'll harm us, and we can sense the sharpness of them or the heat of them, and that tells us to avoid them. Now, when we're going about restoring touch to people, there's a handful of reasons, and we've chosen to use ICMS for a very specific reason. Right here is a simplified sensory motor loop. When you touch an object, let's assume with your finger, the mechanoreceptors in your skin, they deform in some way, and that causes them to generate some spikes. Those spikes ascend the neuraxis via the dorsal root ganglion, spinal cord, a handful of intermediary structures which process it, and then eventually primary somatosensory cortex. And while primary somatosensory cortex is not the be-all and end-all of tactile processing, it is certainly sort of the principal hub for it. And then once you've processed that, you're going to make a decision in some frontal lobe. Do you want to move your hand? Do you want to withdraw your hand, push harder into the object? Doesn't really matter what it is. You make a decision. Then you generate a motor plan that's handled by motor cortex, which then sends those signals back down to the spinal cord. And then the muscles are controlled, which moves the hand, the finger, and generates a new interaction. You get this completely closed loop of behavior and sensation. And so if you were to lose your arm because of an amputation, you could interface with the brain or the nerve directly. There's a lot of peripheral nerve and myoelectric interfaces for that. But in the case of spinal cord injury, you can't access those structures. And so the easiest and sort of most versatile area to access is the primary somatosensory cortex when it comes to sensory restoration. And so with that in mind, there's a couple things that we want to go about restoring. The first is location. Where on your hand are you touching something, right? Which finger are you using? Are you in contact? Are you not? Is it the right part of your hand? Once you've got that down, then you want to know, how hard are you touching something? Are you applying the correct amount of force? Are you pushing too hard, too little, so on? And then what are the features of this contact? Is there a ridge on it? Is there a curve to it or something like that? And then finally, if we're really, really lucky, what's the quality? Again, going back to a picture of my dog, like, is it soft? Is it hard? Is it warm? Is it cold? Those are the kind of things that over the next decade we want to work towards really restoring. And I'm hoping to touch on each of those themes throughout the rest of this talk. Now, because this is sort of a BlackRock webinar, I wanted to give a little bit of like historical context, because we've been using Utah arrays in our participants for years. And there's a big difference between using Utah arrays or any chronic device in an animal or in a person. And with intracortical microstimulation in particular, some of the earliest papers in 1980 and 1990, they already showed that animals could respond to the sensation and that people could perceive some kind of sensation when you delivered intracortical microstimulation to them sort of intraoperatively. But it wasn't until much later when we started doing functional tasks with chronically implanted devices, before everything was very temporary. And in the late 90s is when the Utah array in particular started getting used to show that you could use these devices for long term to produce behaviorally relevant results. In this case, a cat could pick which paddle to interact with based on the stimulation. And then a bit later, we started doing primate studies where you would, again, in this case, implant in visual cortex and start showing that they could, again, respond to stimulation. But really, a lot of this kind of came together where Sleiman Ben-Zmeya, my former mentor, sort of characterized very carefully the perceptual consequences of each of the parameters that you might change with electrical stimulation. And while this is sort of the public-facing version of it, if anyone listening is unlucky enough to have an investigational device exemption document, you might have seen something like this, sort of like this. This is the cover page for the sort of results of a safety study that accompanied the paper on the previous slide, They were sponsored by DARPA as part of the Revolutionizing Prosthetics program, which showed that not only can animals, respond to this stimulation, but it's safe for prolonged periods of time. And because of that work, starting from 1990 all the way through to 2015, that enabled us, this is the same participant as I showed on like the earlier slide, to implant people for the purpose of microstimulation. And then more recently, some of the first visual implants in visual cortex. And so it took, literally 35 years for us to kind of like get to this point where we could do these experiments. And so while the experiments have changed, it's the technology that allowed us to get here. And so with that, I'm going to talk about how we actually go about using these devices to sort of convey those important qualities that we're talking about, starting with location. And again, I want to sort of like emphasize how easy working with humans makes some of these experiments, because if you look back at one of the original papers with ICMS and monkeys for tactile sensation, the only way they worked out to ask the monkeys where they felt these sensations was by stimulating two fingers in sequence and then asking the monkey if it was a rightward or a leftward movement, right? Did the second stimulus occur to the right? You can think thumbward or pinky-ward, or the other. And the monkeys, they did the task, absolutely, but they struggled with it. And it's just really hard to know why that's happening, right? You can't ask them, where on this doll do you feel the sensation? Like there's none of that. And so the interactions you get with the macaques are inherently very limited. In contrast, when we do this with a person, and I hope the audio works, if we stimulate an individual electrode, that's kind of what's shown on the left here, we can just ask them how
This
it
one is
feels.
on the
And I hope people
edge of
can hear
the
this.
thumb right here.
Sure.
It's a
Someone will tell
sharp,
me if they
like a
can.
pin scratching along the edge of the thumb.
So, the participant here, he can just describe. He can just describe how it feels. And we get so much more information from that one interaction than hours of monkey work sometimes. And because people ask, what I just want to preface a lot of this with saying is that a lot of these intracortical microstimulation pulses have this specific waveform where it's biphasic and it's cathodic first. And so all of the charge that we're injecting is inherently balanced so that you're not injecting charge that remains or can harm the cortex. And this sort of waveform came from that safety study. And all the stuff that I'm going to be talking about will have the same general profile, but I'll be changing the amplitude or the frequency of the stimulation. Okay, so this is meant to be a section about location. The participant just described where he feels this on his hand. And so we have to do something with that. So the first thing we're going to do is we're going to map out where each electrode evokes a sensation on the hand. And so this is from one of the earlier papers where at the segment level, what we did is we assigned each electrode to a part of the hand. And you can see that we can really nicely tile the sort of like thumb to pinky range of the hand. And additionally, you can target where you're stimulating. On the right-hand side, we're showing the MRI, where we kind of had expected the sensations to be evoked. And you can see that though it's not a perfect match between them, there's a pretty good correspondence between like what we identified as hand region and the evoked sensations for the participant. Now, when we go about putting this into a functional task, well, we need a bionic hand that has some sensors on it. And in this sort of like simple version of a hand, you might imagine that there's a sensor on each of the fingertips. And in this case, we don't have one on the pinky because this participant doesn't have any pinky electrodes. But then what you do is you say, okay, whenever one of these sort of sensors is activated, well, let's stimulate an electrode that corresponds to that sensation or that location, right? Because we've been able to map out where each participant feels things previously. But as you saw in that thing, it's a bit of a conversation with the participant. They tell us, and something that happens is we give them unlimited opportunities to feel the sensation because what we prioritize is accuracy here, right? That's scientifically that's the most important thing. And what we do is we give them the stimulus, they draw it, we can give it to them as many times as they want. And what we end up with is, these sort of drawings of it. And so here I'm showing two electrodes for two different participants where they've drawn the sensation with their either residual hand or their mouth, depending on how mobile they are. And they give us this like really precise location. but they had a lot of time to make up their mind about where they felt it, and unlimited functionally opportunities to perceive the stimulus. But in real life, if I pick up this can or my phone or something like that, I pick it up once, right? And that interaction is happening very, very quickly. And so there's this question about, do these results generalize? Does this sort of paradigm in which we give them unlimited opportunities translate to sort of a one-shot classification scheme? And to answer this question, to address this potential problem, we had our participants blindfolded, right? So they couldn't see what we were doing. And then just with the robotic hand, we would just squeeze either one or groups of fingers randomly, and they would just have to tell us where they felt it, okay? And then just to speed things up, we also did this programmatically. And what happens is that, yeah, they can do this, okay? So chance is about 10% here, and they could do 50%. So they massively exceed chance levels, but 50% isn't actually like amazing, right? If I pick something up, there's like a 1 in 100% chance that I fumble it and I drop it. And so while there's no doubt that this information is there, that it's informative, it's actually not reaching the levels that we might want our participants to get if they have this sort of actual device in hand. So what do we do about it? Well, if we look at this participant's electrode maps, a thing you may have noticed is that there's a lot of, not redundancy, but lots of electrodes correspond to the same location. They have the same color. There's a lot of red index electrodes. There's several purple middle finger electrodes. And a question we asked is, well, what happens when you pick electrodes that have very similar projected fields, that's the location on the skin where they feel something, and you stimulate them together? So here, what I'm showing is 2 electrodes, right? Each hand corresponds to an electrode. And I've colored in where the participant has reported they feel the sensation. And the color scaling is the frequency at which they report it. So the light blue is they felt it sort of like 1 of 3 times, and dark blue is they felt it 3 of 3 times in this example. And so there's 1 electrode, which is all index, and 1 electrode, which is mostly index, but one time they said it was on their middle finger. And then we can record the projected field or their response when we stimulate both of those electrodes together. And what you can see here is that it's kind of restricted to the union of those, right? And so it's a very intense and focal sensation where they overlap. And that's good. That's nice. Now, the other alternative is you stimulate electrodes where they don't feel like they're not on the same location. And in this case, we can take a pair where it's ring and middle and another where it's index, do the same thing. And what we see is it's not actually the union of them, it's more just the sum of them. And so they kind of add together, and where they happen to overlap or intersect, they're particularly strong, right? Those sensations sum together. And if you use just a basic simple model to predict out how electrodes combine, it does very, very well. And what we can do is then take these groups of electrodes that we've identified as having strong overlapping projected fields, combine them, and repeat that exact same task with the blindfold. And what we see is our performance jumps from 50% median to 95% median, which is much, much closer to what we would hope for a device to have for clinical relevance. Now, a particularly important thing here is that in the single electrode task, they didn't get the fingers wrong, okay? Here are the confusion matrices for the single and multi-electrode task. And what you'll notice is that they're actually on the diagonal most of the time. And especially in the single electrode case, what's really happening is that they're missing a finger. We gave them index and middle, and they only noticed index. Or we gave them thumb and middle, and they only noticed thumb. Some combination like that. And it turns out that what's happening is they're just not noticing one or both of those sensations like 25% of the time. And so really the benefit of this, like the gain in function that we're getting from multi-electrode stimulation, is that where they overlap, the intensity is much more salient so that they can more reliably observe these sensations, and in that rapid one-shot paradigm, know where this contact event is happening. And that difference in intensity conveniently brings me to the next section, right? Because I said we're going to first talk about location, and now we're going to talk about intensity. Now, much like the monkeys, this is from the same paper, this is hard to do, okay? You have to ask the animal over and over again, which of these two sensations is more intense, and you build these curves of intensity between mechanical and electrical sensations. And it's super arduous. In the people, though, the sort of like default way of going about this is you just say, hey, participant, scale of 1 to 10, how intense is this sensation? And you repeat that over and over again for all the different sensations. And what we find really comfortingly is that there's this nice linear relationship between stimulus amplitude and intensity. Now, the downside of this is that these units are completely meaningless. It's like asking me how long is a piece of string or how bright is this screen? And we can't do anything with that across electrodes or between participants. And so what we did is we took some inspiration from the monkey literature and interleaved mechanical stimulation with the electrical stimulation. And so to be clear, we would give mechanical stimulation to a sensate part of the body, right? So that can be the hand or the face in some cases. Combine or alternate the stimuli and ask them to give responses on the same scale such that the intensity range is matched. And then you have these two sets of units, right? So I know from this example electrode that 40 to 80 microamps roughly corresponds to 0.02 to 0.27 newtons of force, okay? And then what we can do is we can convert that for all of our electrodes and say, okay, what do these force ranges look like? Is it the same across electrodes? Is it different across electrodes? And the takeaway from this graph is that one, there's a variety of sensitivity to current, right? ICMS amplitude, but also that the force range that we're looking at is kind of like 0.2 to 0.4 newtons. And that's really soft, right? That's like a couple of quarters or the weight of a USB stick that's just sort of resting on your finger. And so if you think about those localization results, it's not really surprising that, you weren't expecting something there and you just kind of felt it and it was really weak and you just completely missed it. Now, an important distinction is that just because it's weak doesn't mean it's not informative. Okay? So I can tell the difference between a dime, a nickel, a quarter, all on my finger, but I have to be paying attention to it. And so an important question is, how sensitive are electrodes to changes in stimulation in this range? And can you use that for something? And so we can go back to those psychophysical experiments from the monkeys where we ask them to compare two stimuli. So in this case, we deliver a 60 microamp stimulus, and then we deliver another stimulus between 40 and 80 microamps, and we ask them which one was more intense. And we repeat that over and over, average them out, and get a psychometric curve, of which the sharpness this way tells us how sensitive they are to changes in current or ICMS intensity. And the unit we get out is about 13 microamps is the median across our participants and electrodes. And what does that mean? What can I do with that information? So the first thing is that each electrode has its own detection threshold. There's a minimum amount of current required for the person or animal to perceive anything happening at all. It has to get above some kind of baseline or noise floor. And then from that safety study that I showed many slides ago at this point, there's a 100 microamp limit. Okay, and so what that means is you have this range in between your detection threshold and your safety limit that you can operate in, and the number of steps is then defined as that range divided by the sensitivity to charge. And so we can do that for every single electrode across our participants. And what we see is that there's a large range. Again, there's a lot of electrode variability. The spread on that J&D plot kind of shows that. And what we find is that the median number of levels is about 7. And so 7 is, again, pretty good. If you were to ask most people, like, how many levels of intensity do you need? And you just said, is nothing, low, medium, and high enough? Like, that is making a huge improvement over no sensation whatsoever. It is certainly very informative. But we don't want to just do good enough. We want to really restore touch and get back to something meaningful. And if we compare natural touch over the same force range, not just across the full force range, I'm not going no weight to a 100-pound kettlebell or dumbbell, just between that equivalent force range of about 0.4 newtons, regular intact individuals have about 45 levels. Okay, so while we're doing okay with 7, we're still an order of magnitude worse than natural touch. And this is all in a heavily constrained or contrived environment where it's a perfect stimulus, there's perfect timing, everything is super rote, and the participants like know this. But again, regular touch isn't like that. There's a lot of variety. And so to really test this in a real world setting, we implemented a bionic hand where the participants would control the aperture of the robotic hand, and they would grab two foam pucks. And so all they had to do was say which one was hard and which one was soft, right? But what that means is that there's variability, right? Because their neural signals are different every time, which means the opening and closing rate, the total force, those all differ. And then even the way that the robotic hand contacts the foam puck is different on a trial-to-trial basis. And so it builds in all of this real-world variability that we kind of need to understand to really understand if this is suitable for real-world usage. And chance here is about 50%, and our participants were performing at 75% or had a 25% error rate. And so again, we're in this regime of we're doing better than chance, but we're not doing amazingly well. And what that leads me to is a little conversation about, well, how do we encode force, right? As I just said in the previous stuff, everything was super constrained. It was all flat profiles where the current didn't change over time. But here you can see that, well, the force changes as you open and close the hand. So we have to incorporate that because this is a real-time closed loop system. So classically, you might imagine that as you poke your finger, force increases, you hold the sort of object or force there, force is static, and then you release your poke or your finger, and the force goes back down. And so the sort of classic linear way of going about this is that you match the intensity or the current to this force profile. And because stimulus current is equivalent to stimulus intensity, that's really simple. You can just rescale your force trace to your amplitude value. But if you look in the nerves, right, the output of the skin, that actually doesn't happen at all. Okay. Instead, what happens is when the probe or object is indenting and releasing is when all the activity happens. And when it's holding, actually very little is happening. And if you look in cortex for monkeys using a Utah array, if you average out all of the neurons, you get this really stereotyped double peak response. And that just doesn't look at all like the force trace above, okay? And so to test if this matters for ICMS, for force feedback, we kind of repeated that earlier discrimination paradigm where we're asking them which of these two is stronger so we can get the shape of that curve with either linear ICMS traces where it kind of matches that stereotype force trace, or with the biomimetic one with this double peak that's emphasizing the onset and release of the object interaction. And if we compare the psychometric functions, you'll see in this example that the blue one, which corresponds to biomimetic, is a much sharper psychometric function, which means that that J&D is smaller, and therefore your step size is smaller, and you have more discriminable levels for that interaction. And if we compare the J&Ds across all of our electrodes and participants, all of the biomimetic ones have lower values, which means they're to the right of this unity curve. So again, on average, your brain actually just like is better at interpreting biomimetically encoded ICMS trains, right? So that's great. That moves us from 7 levels of discrimination up to 11 levels of discrimination. So, you know, roughly a 50% improvement just from changing the distribution of charge over time. Now, that's good. In the previous section, I said that if you combine electrodes, then you get better location. And here I'm showing that if you change this temporal pattern of them, you get more force resolution. And so it's an important question to work out, well, what happens when you throw these two results together? And so to address that, we kind of did exactly this experiment where we, instead of just doing one mechanical and one electrical, we did each electrode from a quadrant of electrodes. We picked 4 electrodes with overlapping projected fields, stimulate each of them individually or together, and compare that with a mechanical reference. And the key takeaway from this one is you can see that the red multi-electrode trace can actually match the mechanical reference, whereas the single electrode doesn't even come close, especially at the top end. And then you can reproduce these sort of ISO intensity curves, and you can see that all of a sudden, instead of hitting 0.4 newtons, we're able to reach almost 2 newtons of force, which is closer to like an apple, right? So we're still not all the way there, but we have made a massive improvement in the range of forces that you can perceive with ICMS. And not only is the force range bigger, but if you look at the sharpness of those psychometric functions, the J and Ds are also lower. They're much sharper functions. And what that means is that you have a wider range with more steps in it. You haven't like lost resolution as a function of increasing your dynamic range. You've maintained your resolution while increasing your dynamic range. And so we went from 7 discriminable levels with the sort of flat stimulus trains to 11 with biomimetic single electrode, and now we're at 20 discriminable levels, which is only half, right? So we went from 1/10 to half of the relative performance of natural touch. And if we implement this in a closed loop task, all of a sudden our error rate drops to about 7%, okay, which is again much like the location discrimination task. We're getting onto a level of performance where this can actually be used for a clinical device. Okay. Now the next section is sort of like moving beyond that. And everything we talked about, or I've talked about, is about overlapping projected fields. But you don't have to only use electrodes that are overlapping. You can find electrodes where their projected fields are actually adjacent to each other or discontinuous in some way, and do things with that. And this work was really led by Giacomo Valle, who was a postdoc at the time, and he's now a assistant professor at Chalmers University in Sweden. And he really spearheaded this. And so when it comes to shape, the most basic shape there is just an edge, a line, okay? And what we asked our participants was to see if we could work out if they could perceive different shapes or edges on their skin. And so we picked a group of electrodes, or 3 groups of electrodes, that either went across the skin or across the finger, along the finger, or had no clear sort of spatial distribution. And just ask them, hey, what's the direction of this sensation you're feeling with no cueing, right? They didn't really know what experiment we were doing. We just said, what's the orientation? And really nicely for us, they were able to get something like 80% performance across a range of fingers and 2 participants, right? So this like super intuitive sensation that's just there for them with no training and with some pretty simple sort of arrangement of the electrode shapes. And I'm just going to show another video of one of the participants just describing this sensation.
Okay, so this is more of a vertical, but it's diagonal. It's going from the pinky side to the thumb side on an angle across my finger.
So you can just see him saying, it's this angle, and it's like the exact angle that we pretty much predicted from those projected fields and that additive model that I showed earlier on, which is, hey, they combine together, and the participant will just perceive that very intuitively. Now, that is if you do them all at one time, but you can also do them in order, right? You don't have to stimulate every electrode at once, and so we can take those same groups of electrodes and stimulate one after the other to try and create a sensation of something moving across the skin. And in the exact same format, we just say, hey, tell us what you feel, what's happening here. Our participants were able to tell if things were moving up or down or side to side along their finger, and not just the nature of it, but like which direction it was going at all. And not only can you do this within a finger, you can do this with the cross fingers. You might touch something and move your hand across it, or you might move your whole hand across it and it might change from finger to finger, right? And similarly, our participants could just very intuitively tell this. One participant reached like 95% performance and the other was about 80% performance. So they do very well. And next, to really push this, and this is like the start of the pushing ICMS to the limits, is trying to do really like complex stuff. And so we drew some inspiration from the visual literature, where they used ECOG arrays to sort of draw shapes by sequentially stimulating the electrodes to get as complex a sensation as we can. And so Giacomo, he sort of squinted his eyes and picked groups of electrodes that you could kind of convince yourself were letters, and then asked our participants to do the same thing. And again, because we were comparing with the visual literature here, we wanted to know if there's a difference between stimulating all of the electrodes together or in sequence. And what we find here is that while they could do them in both cases, sequential was better, the exact same as the visual literature, which is shown in C. But also that becomes more and more true as the shape gets more complex, because the complex shape is made up of more projected fields, and they can sort of like blur together if there's too many of them at once. And now finally, because again, we always want a functional task, we really struggled to come up with a task in which motion was an informative cue for something. And what we landed on was using a steering wheel, right? Many of you will be familiar, you're driving, you feel your car kind of pull to the left or right, and you adjust the wheel in the opposite direction. And so what we did is we rigged up our participants to control a robotic arm that controlled just like a digital gaming wheel. And then we would simulate the wheel drifting by playing one of those across finger sensations across the robotic hand. And then they would have to respond to that sensation if they felt it at all. This was completely cue free and correct the motion. And here in the middle, you can see that the decoder output in the solid lines and the wheel position in the dashed lines perfectly matches exactly what you'd expect, where if you go one way, they pull the wheel the other way, and vice versa. And on the right, I'm just showing the distributions where you can like really cleanly see where we classified what was happening, exactly where the wheel was. And so it was a very informative and easy signal for them to use for this sort of like regular day-to-day task. And now in the final bit, I'm going to talk about quality. What does a sensation actually feel like? Okay. It is hard to ask someone in the same way that, you might ask, like, do we see the same color red? When we ask a participant what something feels like and they say buzzing, is it the same buzzing that I'm feeling? Is it the same tingling? What does this mean? And how natural is something? And so the person who's actually done some of the best work on this is one of the graduate students at University of Pittsburgh, Taylor Hobbs. And what she wanted to do is, instead of asking this sort of like kind of ephemeral question of how natural does this feel, what she did is she interleaved electrical and mechanical stimulation, similar to what I showed earlier, but instead what she uses the mechanical stimulus as a quality reference, right? And so what she did is she would give a linear ICMS simulation, a biomimetic ICMS simulation, and then the mechanical stimulation in any order, and say which one felt more like the mechanical stimulus, okay? And so what that does is it gives us a ground truth on which of these stimuli actually feels more like the real stimulus. And again, we can pick a sensate part of the body and use that as the reference so that we know that it feels like a mechanical stimulus. And what she found is that pretty much across the board, our participants really felt like the biomimetic stimulus profile felt more like the mechanical stimulus. And like listening to them like describe their responses, what it turns out happens is that the most salient feature of these like pokes is the start and stop. You really don't pay attention to the middle part, and that is sort of like maintained by that intensity profile of the biomimetic stimulus. Now, while she has undoubtedly done the best work on it, a lot of this work is kind of based on that earlier profile I showed you, which shows the average response in cortex to a mechanical stimulus, a trapezoidal indentation. But what this doesn't show you is that if you look at the individual units shown with different colors here for the exact same data set, you actually really struggle to find two units that look like that average. And this sort of like raises this question of what are we doing with ICMS? What's the resolution we're doing it at? And are they equivalent? Do we need to do better than the mean? Or is sort of like recapitulating the mean enough, right? Is that enough for ICMS? Or can we do better? And a thing I'd really like to emphasize is that when we record these signals, you're recording from one, maybe two units, and you can sort them often, right? You know exactly what that unit is doing. If you look at ICMS, especially with a high current, you can activate tens, hundreds, or even thousands of units at a time, depending on whose model you're using, and you're really blasting the system, right? And so it's really hard to know what the benefit is a priori to kind of shaping the stimulation towards individual units. And going back to asking the monkey where it is, it's really hard to ask a monkey what feels better. And so to date, we were completely unable to do this because we couldn't record those individual unit responses and then, replay them back because we didn't know what that template would look like for a person. Now, fortunately, one of our participants is actually partially sensate on his hand, and it's not perfect, but he has pretty good mechanical responses. And what that allows us to do is stimulate his hand and record the responses. And so here's a video. Hopefully you can hear and make out those spikes that are happening while I'm just poking his finger. What that means is that we can record his response to touch. Now, me poking his finger with a cotton bud is not scientific. What we can do is we can repeat that earlier experiment from the monkeys and do repeated mechanical stimulation and just record the responses for this participant in real time. And the biggest thing to note is that you do see this big transient on and off and a little bit of stuff in the middle. This is just repeated stuff on a loop. But you can see that the gist of it is still there, but that it's not just any electrode. The electrodes are doing something subtly different. And this is what it looks like if we just plot the average activity for a single stimulus over time. And it's a little noisy, right? Well, when we're doing ICMS, there again, it's not the same as spikes. Do we account for baseline? What does that mean? What do you do with that information? But it does look like that sort of like monkey response we got from Utah arrays 10 years ago, but we just don't know which ones were meant to target in which way until now for this one patient. And so what we did is we sort of like did a little bit of cleanup on the data so we could get out the patterns that were meaningful for this participant, right, for this specific implant. And what you can see here is that though there is this onset offset, each of those electrodes is doing something slightly different with different levels of activation. Now, what we recorded was spike times, okay? So the sort of simplest way of making a stimulus that is bespoke to this participant is to play back those spikes, right? And so you could think of that as frequency modulation, where the spikes are, modeled after the input we observed. And so in this case, what I'm showing is sort of the equivalent of a raster plot, where instead of, the rasters that I'm recording, these are the stimuli that I'm delivering. So in each row is the electrode or channel that I'm delivering stimulation to, and each tick is a unique ICMS pulse. Now, this is frequency modulation, but up until now, I've really only talked about amplitude modulation because that's where we've had the most success. And so to compare these two encoding schemes, we also developed a version of this for amplitude modulation, where we scale the intensity of the pulses instead of the frequency of the pulses. And so what you can see is that both of these encoding schemes look roughly similar to the data set on the left, but they're subtly different in how the information is encoded between them. And then to make a strong comparison, what we do is we compare those not with linear, because we've already beaten linear, and not just with the average, right? Because we don't want to just stimulate every electrode. We took the average across them and then selected the best 8 electrodes, right? So this is this participant's 8 electrodes which are most sensitive to touch, which presumably means they're the 8 electrodes that would produce the most touch-like sensations when stimulated. And so this really sets up this hard comparison, this sort of steel man of is the mean sufficient for ICMS, or do you derive some kind of benefit for customizing it to the participant? And so similar to Taylor's experiment, we compare the simple or mean encoding scheme and the either frequency or amplitude modulation encoding scheme with a mechanical reference and ask them which one feels more like the mechanical reference. And what we saw is that there was generally a broad preference for especially the amplitude modulation biomimetic encoding scheme. And so what that tells us is, one, that they prefer it over the simple mean that has already beaten the linear encoding scheme. So these are sort of compounding benefits, right? But also, each of these dots here corresponds to a different stimulus, right? This isn't just true for one stimulus. I picked 6 stimuli, and all except one were significantly outperforming the simple or mean response. And so that's where we've gone to. That's where we are. And the future, though, it still has a lot to go. We've done some good stuff for location. We've done some good stuff for intensity, for quality, for shape, but there's more to do. And so the directions that I see this all going is, firstly, adding a proprioceptive prosthesis. I showed that video where the woman didn't have sensation of her skin, but you would have similar deficits if they couldn't feel the location or the conformation of their hand. And this is another thing that our participants are going to have to contend with. Additionally, all of our stimulation has been delivered to area 1 at the moment, and 3B has been completely ignored, and we don't know if there's any functional benefits to delivering stimulation to 3B and 1 together or in isolation, as well as area 2, which might be another target. Then, all of our electrodes are at the same depth because we're using a planar Utah array. That means we're only simulating layer 5. And if we go back to this video, that means that you don't have a lot of control over how the vertical distribution of charge is delivered. And so we're hoping to, have multi-depth stimulation, which will allow us to have less stimulation at each site, but give you better spatial and vertical control over that. And finally, while we have been very successful with targeting the hand and covering the hand, at no point have we covered the entire hand, nor have we ever targeted the arm. And so any device is going to have to cover all of these regions. And so we're going to need, an order of magnitude more electrodes to actually cover this space, as well as probably doing depth. So we need, multiple orders of magnitude to really move towards like amazing clinical devices. And so with that, I'm at time, and I would like to thank everyone, especially the people I mentioned at the beginning, our participants, our collaborators, the people in the lab, and our funding agencies. And so with that, I will take questions.
Awesome. Thank you so much, Charles. That was an amazing presentation. I am sure people got a lot out of it, especially something like touch that most of us take for granted. I'm sure people got away with this presentation with a lot of insights about that particular sensation. We have a few questions, but first we'd like to know the name of your puppy. If that's okay.
Oh, my dog is called Waddles. He decided he was bored of sitting on my lap, even though that's where he's been for the first 45 minutes of the talk. Yeah, he's Waddles. He's a French Bulldog. He's turning 3 years old. He has an Instagram, Waddles the Frenchie. If anyone wants to follow it, you're more than welcome to.
Awesome. All right. So first question we have is DARPA still pursuing prosthetic arm research? Grants and contracts? If yes, what are the major goals of these grants and contracts?
Yeah, so obviously I don't work for DARPA, and nothing I say is representative of them. My understanding is that there are still some DARPA programs. There's sort of like some quirks of the way DARPA funding works, where it's very program manager dependent. And at the moment, their focus is mostly on non-invasive devices, but that changes every few years. So they have a couple programs, but nothing that is immediately relevant to the stuff I'm doing, though I'm hoping that will change shortly.
Got it. Awesome. Are there a lot of these subjective are a lot of these subjective descriptions largely repeatable amongst an individual participant and amongst multiple participants for the same stimulus on the same implanted Utah array?
Yeah, so at a high level, what we're doing is we're implanting area 1 of primary somatosensory cortex, right, which is explicitly a tactile region. And so if you look at the distributions of qualities, I might even have a slide for that, across participants, they're broadly the same. Okay, they're pretty good. Here's a slide for it. So on the right is a sort of word bank that they often use, and what you'll see is that most of them are touch related, right? Even tingling your eyes don't tingle; it's your fingers that tingle or buzz or something. Like those are the sensations you feel. And so this word bank is what all of our participants use and often report sensations for, and those are reliable, right? Now, if you were to go into a different part of the brain, then you would definitely evoke different sensations. But for the most part, the words they use to describe sensations are consistent over time, and the general words they use across electrodes and participants are pretty similar.
Awesome. I think this one's referring to one of the slides. What is the reference of the intensity from 0 to 10 for sensation?
Right. So to clarify a little bit, the reference on those is a mechanical stimulus, right? So if you're doing ICMS by itself, there is no reference, right? But you can just say, give me a number 0 to 10, and then what you're looking for is the relative intensity within an experimental block, right? If I say something's a 1 out of 10, and then I say something's a 2 out of 10, I know that the second stimulus was twice as intense as the previous stimulus. And what you're looking for is changes within. The addition of the mechanical stimulus is what gives you that ground truth that allows you to actually give you a real reference and a real meaningful unit to derive for those sensations.
How much stimulation can the brain tissue of a person tolerate? Is the 100 microamp level arbitrary? And what would going above this improve function with a wide variety
Yeah,
of
that's
percepts?
that's a great question. There's a couple of sort of like interactions there. So the first thing is it arbitrary? Kind of yes, right? The safety study is what set that limit, and no one has really seen any reason to go above it. The second thing, though, is if we go back to that sort of animation I had with the so this like simulation of the spread of ICMS, what you'll notice is that I think this is simulated to be like a 40 microamp thing. 100 microamps is activating a huge volume of tissue, right? And so going above 100 microamps just means you're stimulating a broader volume, which may be more intense, but it also means it's less precise, right? And so while it might give you more intense sensations, my personal opinion is that what you actually want is smaller charges that are better distributed throughout cortex instead.
Are you planning on repeating some of this with a slanted Utah electrode array?
Yeah, I mean, so what I can say is I'm not, mostly because there is a specific somatotopy in the brain, okay? And so if we go back to this slide, what you'll see is along that sort of vertical axis, which is medial lateral, you're changing the location over which the brain is representing a part of the body, or the electrodes are feeling something. And so what that means is if you have a single slant, it doesn't really matter the orientation. As you change depth, you're also moving location. And so really to sort of do the multi-depth stuff that I'm describing, you actually need either some sort of staggered layout where you're alternating depths with a very close spacing of the electrodes, or electrode arrays that have multiple contacts along them. And I can say that I am trying to do those kind of things, but the technology is less reliable than I would like at the moment.
Awesome. Is temperature another dimension of sensation that you'd be interested in characterizing in the future?
Yeah, absolutely. What I'll say is that there's actually a little bit of contention in the field about whether temperature is at all represented in somatosensory cortex. There's some rodent literature that says it is. There's some human literature that says it is, mostly with fMRI. But when we do this stimulation, it is very, very rare that we actually ever get temperature percepts. I think it's at like 1 or 2%, and even then, it's not consistent across days. When I showed those sort of tingling, buzzing, pressure sensations, those are very consistent. The temperature ones don't really seem to be evoked by this. Now, there are other parts of the body that undoubtedly will evoke these kind of sensations. And one goal down the line is to identify those regions so that we can create more reliable percepts. And I should add, though it's not relevant to spinal cord injured people, there have been a couple papers recently where they've shown that you can evoke thermal sensations with some peripheral nerve stimulation or some skin stimulation if you're really careful. And so it's definitely an aspect that we need to work on, but it's a little farther down the line.
Got it. So I'm going to summarize. It looks like there's a lot of interest in this particular topic. I'm going to summarize it. So basically, how limited are you and your consortium by biphasic stimulation waveforms? And are you looking at other different shapes? The waveform?
Yeah, I mean, so biphasic. Well, okay. I would preface this by saying I'm not an electrical engineer, and nor am I really a neural engineer. I came at this from a basic neuroscience and psychophysics perspective. So the first thing with biphasic stimulation is if you don't do it and you don't balance your stimuli, my dog wants to come on my lap again, right? Then what happens is you're leaving residual charge in the brain, and that's actually what risks causing neural damage, especially over longer periods of time, right? So biphasic stimulation is limited in the sense that it's safe, right? But I don't think that the biphasic nature itself is giving us any specific limitations. That said, there's a decent amount of work on sort of like voltage shaping, and what might become useful and something that we're interested in pursuing is looking at sort of like differential charge across nearby electrodes, where you're creating a field across electrodes as opposed to a point source that originates from a single electrode.
Got it. Got it. Also, going to ask another question by combining a few, and it's also something I had in mind. Can you comment on the context-dependent nature of touch? Meaning, if whether someone's paying attention to it or not, whether, what maybe the touch encodes different levels of
Yeah,
reward.
absolutely.
And yeah.
So what I don't unfortunately have a slide for that, but what I will say is that another collaborator at University of Pittsburgh recently put out a paper on the archive. Her name's Ceci Verberschot, And what she did is she had participants interact with sort of like avatars of textures while they were getting stimulated, and examined the extent to which that visual context influenced their percept. And what I can say is that it was incredibly and impressively strong. And so
Wow.
what that means is that the visual context and your sensory expectation is probably going to be a huge component of how these sort of like prosthetics interact with us and our perception. And that's true for touch as well, right? And so that isn't a thing that we haven't been able to fully characterize yet because there's a lot of context, etc. But it is definitely a strong and impressive effect.
Got it. In the experiments that compare the intensity effects of ICMS versus mechanical stimulus, is it challenging for SCI participants to perceive a mechanical stimulus? And do
Yeah.
these participants have some residual sensory function left?
Yes. So I won't say it's difficult per se, just because the participants we tested this on both had some residual sensation in their hand. So the participant that I showed the poking of, he has pretty good residual sensation across his whole hand. And the other participant that Taylor tested this on had good residual sensation on his thumb. And so it's not difficult, but it's a thing that is just either you can do it or you can't do it in the same location for your participants. But it's not trivial to set it up on the skin, on the face, as long as the participant is comfortable with that. So difficult, no, because people are relatively good at sort of just like giving you numbers. You could, if you really wanted, kind of compare brightness and sort of loudness or ICMS intensity. These are all things that you can ask people to do, and they'll get a sense for it. But it's not trivial either, and it definitely helps if they have residual sensation in the location you're trying to stimulate.
I think this question would help a lot of companies like us. What is your ideal electrode in terms of coverage, surface,
Yeah,
depth,
it's
function?
a great question. And I definitely don't have all the answers. One of the things I don't have here, right? But if we look at the somatotopy, right, that the hand takes up a huge portion of the brain, of somatosensory cortex. And the hand is the most important, and that's definitely where we need to focus on if we're talking about upper limb prostheses. Feet are different. So the questions are for coverage is you need to cover everything. But as you go to away from the hand, the sort of spatial resolution also decreases, right? Smaller and smaller parts of the brain are used for the arm or the back or the legs. And so you don't need your electrode necessarily to change because the brain is changing already, right? So I think from a coverage perspective, we're probably okay with even the current spacing. More is always better, but I don't think that it'll give us like sort of qualitative differences. The issue actually becomes if you look at these pictures in the middle, the vasculature of the brain is really heavy, right? And so a thing that happens is we'll plan to put our electrodes in a specific location, and then we open them up, and then there's just a blood vessel kind of in the way. And so you have to move the electrode. And so really the things that we're looking for is the ability to put more electrodes in. If I had unlimited resources and opportunities, I'd probably just put in like 10 arrays in sensory cortex, all of them like fully wired and densely spaced. But they would also have to be small enough that I could move them around and fit them in between the blood vessels. So that's the kind of thing that I'm personally looking for is small modular systems with high density that I can move and position specific to that participant's morphology.
Got it. And do you see any limitations with the current stimulation amplitudes that you're able to administer?
I don't think so. Like I said earlier, going above 100 microamps only just means you're activating more neurons, right? And I don't think that more is always the answer. I would rather I'd rather use a scalpel than a hammer when I'm delivering stimulation because I think that that's going to be the future towards delivering realistic sensation. If sort of, if I go back to this result where this like bespoke stimulation, which is like operating on the scale of millimeters, is better, then I'd like to think that if I can actually address and stimulate the circuit much more carefully, then I think that I'll be better as well. So amplitude above 100 microamps, ideally I would never have to go above 50 microamps, but I can distribute that charge very carefully instead.
Got it. I'm going to do the last two questions because we're at time and we have so many more, and I will email you the rest. What is the current latency, say the time it takes from the initiation of intent to bionic arm movement?
Yeah, I mean, well, that's an interesting question, right? Because the simple answer is that actually you can have negative latency when this happens, right? If you think back to some of the really early consciousness experiments, like you can decode from the brain when someone wants to move before they want to move, right? That's a thing that you can do. And so in theory, you can have negative latency where you can just start moving the arm ahead of time. The issue becomes more of a signal to noise ratio question and how are you implementing your decoder? And so, you know, on average, it's probably 100 milliseconds because like what we want is really high confidence that they want to move and what direction they want to move it. If you just want to know if they want to move at all, that you can know before they've even consciously processed that thought. And I know that's maybe like a little bit confusing because you're doing it before they want to move, but it's actually when they've started that thought process it's possible.
Got it. Last question. I'm very interested to know your comment on this. How valuable would a healthy individual with a Utah electrode array or similar be implanted for your research or in this field be general?
Yeah, I mean, it would be incredibly useful. I mean, the stuff that's on screen at the moment is a really good example of that, where this is the first time that we've been able to work out what like degree of variability there is in a person and whether this is meaningful perceptually. And so this is, showing 2 arrays in S1 and only in area 1, really. And so if we were able to have a fully intact individual whom we could really communicate with versus a monkey, which, we can do some amazing work, but it's really arduous, you could truly accelerate the rate at which we're able to do this kind of research, like at least an order of magnitude.
Awesome. All right. We're already 2 minutes over time. It looks like there's a lot more questions to cover. I will make sure to pass all of your questions to Charles, and he'll be more than happy to answer it. And thank you so much, Charles, for your time. And thank you for sharing the details of your seminal work and pushing the field forward. These are exciting times, and BlackRock is stoked to be partners with you in your endeavor. Thank you so much again.
Thank you very much for having me.